Hi everybody. So these are the notes for Chapter 5. We're going to start at the beginning. I know that I already went through most of this with, or quite a bit of this with both classes, I believe, but I thought it'd be better if everything was in one spot. So we go back to the beginning where we're going to talk a little bit about energy. And energy is defined as to cause change or to do work. Energy that we use to cause an object that has mass to move, that's called work. There's not a lot of that in chemistry, but there is a little bit of it, like when gases expand and like that. And then energy that causes the temperature of an object to rise, that's what we refer to as heat. So we split energy up into two categories, into potential and kinetic energy. Potential energy is stored energy that's due to composition or structure. So what this stuff is made of and how the atoms are actually linked together, that's what we mean by potential energy. Kinetic energy is due to the motion of small particles in a sample of matter. Oops, kind of skipped ahead there. So it's it's essentially, for our purposes, it's heat. It's the energy that's due to materials that are moving around, and the hotter they get, the faster that they move. And then the units that we're going to use for energy are called the joules, and we use a capital J to distinguish what a joule is. There's also another unit we use that's referred to as a calorie, where 4.184 joules are equivalent to 1 calorie. This is the same type of calorie that's used in, I keep skipping ahead, I don't mean to. This is the same kind of energy that's used in the nutritional value of foods, except that those are kilocalories instead of just plain calories. All right, so we're going to start out with what's referred to as the first law of thermodynamics. And the first law of thermodynamics says that energy can't be created or destroyed in an ordinary chemical reaction, but that it can change form. So the potential energy that's stored inside of an object due to what it's made of, I can rearrange those atoms and release some of that energy as heat. So we use the internal energy to keep track of how much energy there is in a system. And the internal energy will be the sum of all of the kinetic and potential energy that's present in my system. So if I want to change the internal energy, the first law of thermodynamics tells me that I can't really change it unless I do something to it. So if I actually do work on it or add something to it, that's the only way that it would change. So we use the symbol capital E for internal energy. So if you look at this equation, the delta E there is talking about the change. That delta sign means the change in the internal energy is equal to heat and work. So energy has to be exchanged with my system, and it can be exchanged only as heat or work. We use a Q for heat and a W for work. Anything that goes into the system is positive. Anything that comes out of the system, so if my system releases heat but goes the other way, then it's gonna be negative. The same thing with the work. If the system does work, so if the work is done by the system on the surroundings, it would also be negative. Specifically, when we talk about heat and the heat that's absorbed by the system, we frequently refer to a system as being endothermic or exothermic. So when it's endothermic, that means that heat is being absorbed, and when it's exothermic, that means that heat is being released. So we're going to use that little equation, the delta E equals Q plus W, and calculate the change in internal energy for two processes and decide if they're endothermic or exothermic. So the first one says a balloon is cooled by removing 1 kilojoule of heat, and that it shrinks as the atmosphere applies 382 joules of work to it. So there's my equation. So what I want to do now, I want you to stop and think about what you want to plug in for Q and what you want to plug in for W. You can pause the recording while you're thinking. So you notice that I changed the Q from 1 kilojoule to 1,000 joules because my units have to match. I can't add joules and kilojoules. Got to have the same units. So minus 1,000 plus 382 joules equals negative 618. So I want you to see if you can do the same thing for this one underneath. All right, so system absorbs 25 joules of heat and does 10 kilojoules of work on the surroundings. There's my equation. Remember, you can pause. So I have 25 kilojoules of heat that it absorbed, so it's positive, and it did 10 kilojoules of work on the surroundings, so that's negative. So internal energy and the next topic we're going to talk about, which is enthalpy, are both what we refer to as state functions. So state function basically means that the energy or whatever the particular variable is we're talking about that's possessed by a certain substance, okay, is only dependent on the conditions that it's at. So my beaker here in the middle, where I've got this 50 grams of water at 25 degrees Celsius, has a certain amount of internal energy. And the idea is that it doesn't matter whether I cooled the water down from a high temperature or whether I heated it up from a low temperature. The energy it has only depends on the conditions that it's at, and that's what we mean by a state function. So internal energy is a state function, all right, but the way that I use the energy is not. So what the Q and the W, those are not state functions. So they're showing you a picture here of a battery, and the battery possesses a certain amount of energy, essentially based on the size of the battery and the chemical reaction that's taken place inside of it. So if I take two identical batteries and one of them I short out. So up here I basically just hooked the thing up so that there's a wire going to each side of it. And in the other one I've attached it to a small fan. So what'll happen in the one that has been shorted out is that all of the energy will get converted into heat. So everything that was inside the battery gets turned into heat. Whereas in the other one, some of the energy will be used as work to turn the little blades on the fan so that the blades on the fan are going around. But the amount of energy that's lost is the same in each case. So the amount of energy, that's a state function, and the Q and the W are not. So I want you to look at each of these following conditions and see if you can figure out whether they would be essentially state functions or not. What we're going to be looking at is whether they're dependent or independent of the path taken. So take a minute, think about each one, all right, and then kind of fill in what you think, whether it's dependent or independent. Remember, you can pause the video. All right, so the last one, I feel like I kind of am missing the screen down here at the bottom. There we go. The last one is dependent on the path. So the next variable we're going to talk about besides internal energy is enthalpy. So we give the enthalpy the symbol capital H. And enthalpy is the change in internal energy at constant pressure. So in the problems we're doing, where work will be zero, so we're not looking at pressure volume work, then essentially the change in enthalpy is equivalent to the change in heat. So the change in enthalpy, or delta H, is always determined as the enthalpy of the products minus the enthalpy of the reactants. So if you look at this little graphic on the side, if I think about this as a combustion reaction where methane and oxygen, so here's my reactants, goes to carbon dioxide and water, there's my products down at the bottom, then my enthalpy change would be minus 890 kilojoules. If I go backwards, so if I go this way, essentially from carbon dioxide and water to make methane and oxygen, then my enthalpy change is going to be positive. So I have the same magnitude, the difference is the same, but it's negative in one direction, which means it released heat, and positive in the other. So enthalpy is an extensive property, and this is going to be an important point as we go through calculations. So it depends on how much stuff is there. I always like to use the example of if you're standing around a campfire and you got a log burning on the fire and you're cold, you put another log on the fire, all right? So 2 logs, twice as much heat. It's the same idea. We can calculate the amount of heat used to carry out a certain amount of a reaction, and then we can kind of relate it to the amount that we actually want to know about. Delta H for reaction that's carried out in the forward direction is going to be equal in magnitude and opposite in sign. So if I reverse a reaction, the magnitude, the size of the number stays the same, but the sign will be different. And then last of all, the delta H will depend on the states of the materials that are involved. So when I'm trying to figure out what the enthalpy changes for a reaction, it's different if I look up my reactants and products in different phases. Okay, so I have to be careful that I always look at the same phases when I'm doing that. So we're going to use something called calorimetry to calculate the heat of reactions. So experimentally, and this is actually the type of a reaction that you guys will be doing in the lab that we're simulating for you. So wait a second, I'm going to go back a second. All right, so in calorimetry, what we do is we isolate our reaction and we make the assumption that we can keep track of where all of the heat is going. So the way that we typically would isolate a reaction, all right, is by putting it in a cup. We're going to need some terms in order to do this. We're going to need to know what we mean by the term specific heat and the terms heat capacity. So specific heat is the amount of heat I need to increase the temperature of 1 gram of any substance by 1 degree Celsius. So I can look that up. That's something that is tabulated. Those values are available. I can look them up. There's a small list down at the bottom of this slide, as a matter of fact. Heat capacity is different. So specific heat is different than heat capacity. Heat capacity is the amount of heat required to increase the temperature of an object by 1 degree Celsius. So there's no mass involved in it. It's for a complete object, and it's usually determined experimentally. The units on these are different. So the top one has units of joules per gram degree Celsius, and the bottom one just has units of joules per degree Celsius. Okay? So based on those definitions, I can come up with some equations that let me calculate heat. So specific heat is the heat transferred divided by the mass times the temperature. And if I rewrite this, solving for Q, I get Q is equal to mass times specific heat times the change in the temperature. I can do the same thing with an equation for heat capacity. So for heat capacity, I can determine that the heat capacity is the heat transferred divided by the change in temperature. And so I end up with Q is equal to, we use the symbol capital C for heat capacity, times the change in temperature. Okay, those two equations will be very useful when we're doing calorimetry problems. So this is a simple equation. It's asking you how much heat is required to heat 125 grams of water from 25 degrees to 78.6 degrees. So I start essentially with my equation, and I plug in my variables by reading through my problem. So 125 grams of water, that would be my mass. My heat capacity, I looked up on that little table, and then my change in temperature, always final minus initial when I do my change in temperature. And I get 2.8 times 10 to the 4th joules. We're going to talk about constant pressure calorimetry in the next part of the notes. So in part 2, you'll be looking at the next few slides and how we carry out calorimetry experiments and use those equations that we just went over. So again, I want to remind you, go back through the video, watch it as many times as you need to, pause it, work on problems, see if you can figure out how to plug things in and like that. All right, take care.